This is the third in a series of resources on integral calculus. We define the idea of an integral. We investigate the fundamental theorem of calculus and look at some basic rules for integrals. We explain the difference between definite and indefinite integrals looking at a basic example. We consider using Riemann sums as a method for approximating a definite integral. We investigate the integrals for specific function forms, including polynomials and trigonometric functions. We will also look at substitution methods to simplify certain integrals. In previous resources, we realized that there were two different ways to consider an integral. The first was a graphical interpretation of the integral, in which we find the area between a curve and the x-axis. This interpretation will lead to a definite integral, which has a particular region of integration. In the general definition, this is between the x values a and b. We initially considered an integral as an antiderivative. That is, we knew the function was the derivative of some function, and we wanted to find the original function. This will become an indefinite integral. First, let's consider the definite integral. Suppose we want to find the integral from 1 to 5 of the function 3x squared with respect to x. We seem to recall that a derivative lowers a power by 1. So as an initial guess, we think that the antiderivative of 3x squared might be 3x to the third power. To check whether or not we were correct, we take the derivative of 3x to the third power with respect to x. We have 3 multiplied by 3, x raised to the power 3 minus 1, which simplifies to 9x squared. Perhaps a better guess would be that the integral is just x to the third. Let's find out. Taking the derivative, we have 3 multiplied by x raised to the power 3 minus 1, or 3x squared. So we have found our integral. So to find the area, we have x to the third evaluated from 1 through 5. We have 5 to the third minus 1 to the third, which results in an area of 124 square units. What if we want to generalize? What if we want to find the antiderivative for 3x squared, but not limit it to any specific region? We saw in the definite integral section that x to the third power is an integral for 3x squared. Is it the only function whose derivative is 3x squared? What about x to the third power plus 5? Recall that the derivative of any constant is 0. So we have 3 multiplied by x to the power 3 minus 1 plus 0. This simplifies to 3x squared. So x to the third plus 5 is also an integral for 3x squared. What about x to the third minus 7? Is this also an integral for 3x squared? Taking the derivative, we once again get 3x squared. So this is also an integral for 3x squared. To find the integral of 3x squared, we need to consider the fact that we can add on any constant we want to the x cubed. So the indefinite integral of 3x squared is x to the third power plus c, where c is any constant. Let's summarize. The definite integral provides the area between the curve and the x-axis. There is one specific numerical answer for a definite integral. The indefinite integral is more general. It is the antiderivative for a function, without any limits. The answer for an indefinite integral takes the form of a function itself. To form the indefinite integral, don't forget the plus c.